Now today we are going to start the noble gases. We used to call them as inert gases, and we know that the main source of noble gases is the atmospheric gases, which contains around 1% of the total volume of the gases. So the noble gases, we used to say that they are separated by, that is, fractional distillation, because they are having the different freezing point and that is boiling point, because of the van der Waals forces which is present in the noble gases. So what we used to say that we'll discuss about the noble gases. The elements of the noble gases are, we used to say that it is, write that helium, neon, then we can write that argon, then we can write that krypton, then we can write that xenon and the radon. The radon is radioactive. So this is radioactive. We know that it is radioactive. We used to say that. So this is, that is a radon, which is a radioactive. We used to say that it is a radioactive. And so generally we won't used to study that the compounds of radon, but recently we know that the compound of radon is also formed, that is the fluoride of radon, that is RnF2. But we'll say that these are the noble gases, the helium, the neon, argon and krypton as well as the xenon. And this is radon. Then radon, that is the electronic configuration. If you write that it is the electronic configuration, then in that case of electronic configuration, we get that in case of electronic configuration, we can say that it is N2p6. So that is the electronic configuration what we used to write for these gases. Now they have 8 valence electron except that helium. Now we can write their occurrence. So if we talk about that occurrence, we can write that, as I have told you, that the occurrence of these noble gases, we can say that occurrence except radon. We used to say that except radon, that is Rn, all are present in, all the others are present in the atmosphere, So that is that they are present in the atmosphere. We used to say that all other except that radon, they all are present in the atmosphere. In dry air they are atmosphere, and in the dry air we used to say that in the dry air they are 1% by volume. Dry air they are 1% by volume, we used to say that. So that is how we can write that the inert gases are present in the atmosphere. All the inert gases are present in the atmosphere except radon. Radon is radioactive in nature. Next we can say that argon is in most abundance. Argon is most abundant gas which is present in the atmosphere. So we used to say that argon is the most abundant which is present in the atmosphere, and we say that helium and neon are found in radioactive origins. So helium and neon are found in the radioactive minerals. So the radioactive minerals, we used to say that radioactive minerals, that is pitch blende. So minerals like we say that is we used to write that it is pitch blende. So that is pitch blende, we used to say that. So it is the pitch blende, that is the ore of uranium. The pitch blende is the ore of uranium, and then we can write that monazite. That is monazite is we used to write that these are the monazites. We say that monazite is a phosphate of that is cerium. So it is phosphate of cerium. We used to say that phosphate of cerium. We used to say that is monazite. Then we write that it is clavite. So that is clavite, that is called clavite. We used to say that clavite is the That is an ore of uranium. So it is called uranal night. So it is that is what we used to say. That is also called as uranal night. That is we used to write that impure radioactive substance. So it is impure radioactive substance. That is radioactive substance. That is called. We used to say that the radioactive substance called as that is uranal night. So that is uranal night. We used to say that. So that is the radioactive substance, etc. These are some of the minerals in which that they are present. So these are the minerals in which the radioactive elements are present. So we used to say that the radon is formed as from the decay of radium. The radium, which is that is having 226. That is we used to write that it is 226, and its atomic mass is 226, whereas its atomic number is 88. It decomposed to give radon plus. We get the helium like this. That is how we are able to get that the radon, and we write that it is 222. So that is how we are able to get that the helium is. So helium is generally formed in the radioactive decay reactions. In all the that is radioactive reactions, the helium is present. So you can say that the main source of helium will be the gases which are formed from the decomposition of the natural decay series. So we say that the main source of helium is the right disintegration series. Is the gas produced from disintegration series of radioactivity. So from radioactive disintegration series. So that is a disintegration series, we used to say that. So that is the main source of that. The radioactive disintegration series, we used to say. So that is the main source of that is helium, we used to say that. Because helium gas is produced in thorium series, in the uranium series, in the neptunium series, as well as in the actinium series, what we have discussed in the radioactivity is. So in all the series, the helium is emitted there. So that is the main source of helium is. So we say that which is disintegration series. So the main source of helium is the gas produced from the disintegration series in the right. Helium is the gas produced in this. So in the atmosphere, we used to write that. So that is the main source of helium. We used to say that. Now we can write that this is about that the source, the occurrence of these elements is. So that is what we have written about the occurrence of these elements. Next we can write is, we can say that is the physical properties of these elements. So we'll write that the physical properties we can discuss. The physical properties of these elements, we can say that about the physical properties of elements. Properties of elements, we used to say that. Then if I write that physical properties of element, I won't have to discuss about the atomic radii of those. So the atomic radii, that is increases from top to bottom in that group. So it increases from top to bottom in the group. It increases from top to bottom in the group. We used to say that. Bottom in a group, we used to write that because the size increases. Similarly, we will write that since the van der Waals forces increases from top to bottom, so the melting point as well as boiling point both increases from top to bottom. So we'll write that. Another is the melting point and the boiling point. So if I write that the melting point and the boiling points, we used to write that both increases from top to bottom because the surface area increases, so the van der Waals forces increases. So both increases from top to bottom. So both increases from top to bottom because the surface area increases from top to bottom because the surface area increases. Since the surface area increases, so van der Waals forces increases. Surface area increases, the van der Waals forces. So the van der Waals forces, we used to write that. So that is how we can write that the van der Waals forces and about that the melting point and the boiling point is. So now if we talk about that, the electronegativity, obviously we'll say that from top to bottom the electronegativity of these elements decreases. Then ionization energy, it decreases from top to bottom. So we can write that, suppose we say that for these, we'll say that the electron affinity, now we are going to write that. So if we talk about that electron gain enthalpy for these elements. So if I talk about that, that is the electron affinity we are talking about. So electron affinity, that is what we used to say that the electron affinity. Then we can write that for these elements, the minimum electron affinity is for neon. And the maximum electron affinity we used to write that is for helium. So actually the helium has maximum electron affinity, then it is radon and then it is xenon, the electron affinity. Then we used to write that the argon and the krypton is almost same, and the least is we used to write that it is neon. Neon has minimum electron affinity. So the value is positive for all. The delta H value it is positive for all. We used to say that addition of electron in case of all is an endothermic phenomena. So addition of electron in all is endothermic phenomena, but it is more endothermic in case of neon as in case of helium is. So that is how we are able to write that the electron affinity data for these elements, because they are having complete helium having complete duplet, but all are having the complete octet. So in that case they have less electron affinity. Now we can write that the atmospheric content of these elements is what is the percentage they are present in the atmosphere. So the atmospheric content we used to write that the atmospheric content we already know that the atmospheric content is maximum for argon. We already know that because atmosphere contain maximum argon, then it is neon. So it is argon, then it is neon. We say that the argon is maximum present in the atmosphere. So argon is present maximum in the atmosphere, then it is krypton, then it is helium. Then krypton we say that, then it is helium, and then it is xenon. Xenon is present least in the atmosphere. So according to that abundance, they are right. Their availability is less. The argon is available in the maximum quantity. So that is the abundance of those in the atmosphere. Next we can write that they are colorless, odorless and tasteless gases. So we can write that solubility in water. They are, we say that they are colorless, odorless, we used to say that, odorless and tasteless gases which are sparingly soluble in water. Sparingly soluble in water, we used to say that. So sparingly soluble in water, they are least soluble in water, we used to say that. So they are sparingly soluble in water, we used to write like this. Next we can write we used to say the colorless, odorless, they are tasteless gases and they are sparingly soluble in water. The solubility in water, no doubt that is less, but we can write that they are less soluble. Now we can check that the boiling point of these. Helium has a lowest boiling point. Helium has a lowest boiling point of, that is boiling point of 4.2 Kelvin. So it has the boiling point of 4.2 Kelvin. It is very less. So helium has a boiling point of 4.2 Kelvin of any known substance. We used to say that. So in all substances, the helium has the minimum boiling points. All known substances. Other also have very low boiling point, but they have due to the weak dispersion forces. As I have told you, they all have weak London dispersion forces. So others also have the very less boiling points, very low boiling points due to weak London dispersion forces. Due to weak London dispersion forces. So dispersion, we know that it is forces. So the dispersion forces, London dispersion forces, they are operating to very less distance. It is the forces inversely proportional to r to the power of 6. So they are very weak. We've already discussed those forces. So they contain the very weak London dispersion forces, but we used to say that the boiling point and the melting point, we used to write that it is depending on the surface area. So we used to say that, as I've told you, that the boiling point and melting point you can write like this. Due to that, you can say that the boiling point is, so boiling point and the melting points both in these cases is xenon will have more boiling point than it is, we used to say that, than it is krypton, then it is argon, then it is neon, then it is helium. So it depends on that is the size of the gases, because van der Waals forces, the London dispersion forces, that is depending on the size of the molecule. It depends on the size of the molecule. Larger the size, more is the surface area, more will be the boiling point. So like that, we are able to write the boiling point of these gases is. Next we can write is, now we can discuss about their chemical reactivity, the chemical properties. So these are the, we'll say that, obviously we want to discuss about the ionization energy, because all will have very high ionization energy. So all will have very high ionization energy. It decreases from top to bottom. So if we talk about the ionization energy, then we say that in that case, ionization energies, so they all have very high ionization energies. So they all have very high ionization energy. They have, that is, ionization energy of helium is greater than neon, is greater than argon, is greater than krypton, is greater than, we can write that, that is xenon. So like that we are able to write that their ionization energies are. So their ionization energy we can write like that. So that is about the physical properties of element. We can write the chemical properties of element now. What is the chemical properties of element? Let us check that. So we can write that the chemical properties of elements now. What is the chemical properties of element? Let us check that part. So if we discuss about the chemical properties of element, that is the chemical properties of element, we say that properties of elements, we'll write that. So to discuss about the chemical properties of element, if we discuss about the oxidation state, then it is of no use to discuss about the oxidation state, as the P subshell or the S subshell is completely filled. So it doesn't discuss that what is the normal order of oxidation state they used to show. It is only the compound which it can form, and on the basis of the electronegativity difference, we can say that we can decide the oxidation state in that. So let us check that. We'll say that the chemical property, for that we can first write the reactivity. So radon is most reactive in all of these. So I'll write that first, what is the reactivity order of these gases. If we talk about the reactivity order of these gases, we used to say that the reactivity order of the gases, then in that case we are able to write that the reactivity order of the gases is, as I have told you that radon is maximum reactive, then it is xenon, I will say that that is more reactive, then it should be the krypton, that should be more reactive. So then it is krypton, then it is argon, and then it is helium, we can say that. And neon is the least reactive one. The reason is it doesn't have electron affinity. So electron affinity is it is most endothermic. So it doesn't form the bonds with it doesn't accept the electron, neither it donates the electron. So the reactivity order for this is, for these gases, is like this. So that is the reactivity order, we can say that for these gases. So next we can write is that is they are least reactive because of that these gases are, we used to say that gases are least reactive because of their complete octet or duplet, due to the complete octet, or you can write the duplet, complete octet, or octet, that is NH2P6. NH2P6 and duplet in case of helium, that is the duplet, we used to write that in case of helium, duplet, that is helium, that is 1s2, and we used to say that they have high ionization energy and low electron affinity. So they have high ionization energy and low electron affinity. So that was the reason they are very less reactive. Their octet is complete, and we say that their high ionization energy is very high, and their electron affinity is also very, very less. We used to say that. So next we can write is the compound. The very first compound of that xenon is formed by Neil Bartlett. So let us check that how that Neil Bartlett has formed the compound. So we used to write that while that is the we say that the very first compound, very first compound of xenon that is formed by Neil Bartlett. So it is that the Neil Bartlett that has formed that is the very first compound of xenon. So actually what happens that he is preparing a compound that is Bartlett. Actually what happens, he is preparing a compound, he prepared a compound of oxygen. He prepared a compound of oxygen with platinum fluoride. Platinum fluoride as that is O2PtF6. He is preparing this. So he prepared this compound first, that is O2F right now. O2PtF6, that is what he has prepared. So he prepared this compound is first prepared by him. So he prepared this compound in the laboratory, and he thought that the ionization energy of. So he get an idea. That the first ionization energy of O2 oxygen is 1175 kilojoules per mole. And what he thought that the first ionization energy of xenon is first ionization energy of xenon is also that is similar to that of oxygen, and he told that it is 70 kilojoules per mole. So 1170 kilojoules per mole. So what he has done, he has replaced that oxygen by xenon. So he got the first compound of xenon. So thus he replaced the oxygen by xenon in the chemical reactions. Thus he replaced the oxygen by xenon. So when he replaced the oxygen by xenon, he got that in the reaction as we used to say that it is xenon plus PtF6. So they got that is what we got is xenon PtF6. We got this as a compound, the very first compound. It is a red color compound. So red in color compound. So this is the first compound which is formed of that xenon is by the Bartlett. So he prepared the red compound this by mixing xenon and PtF6. So that is how we get the very first compound of xenon, the red color compound, but we get that. So the first compound of xenon formed by the Bartlett is this. So Neil Bartlett, he prepared this. The other compounds studied are, we can write that, the other compounds studied are, that is KRF2, KRF4, RNF2. These are few more compounds of other noble gases which are studied in detail, but not this is studied in detail, but this is not yet isolated. It is only identified in the spectroscopy methods. So this is studied in detail, but this is not isolated. not isolated. So I write that. Just write there for this. I'm going to write that this etc. is studied in detail. And the compound we used to write that that is RNF2 is only right studied spectroscopically, that is only studied spectroscopically, but not isolated. So it is not isolated, but it is studied spectroscopically. So that is how we can write that. These are the other compound that is right. That is not isolated, but it is spectroscopically. We have seen that RNF2 is prepared there. And if radioactive that is tracer technique also, we have found that the RNF2 exists. But no true compound of neon and argon is that is neon, and we used to say that helium is yet studied. Recently in 2000, one of the compound of argon has been studied. So we can write that recently. We can say that recently one of the compound of recently we can write that one of the recently in 2000 the one of the compound of argon is studied. One of the compound of argon is studied as argon, that is HARF, argon hydrogen fluoride. So that is argon hydrogen fluoride is studied. Hydrogen fluoride is discovered. So this is one of the recent molecule of argon that has been discovered, and it is stable. It is stable. So that is discovered, and it is stable in nature. So it is stable also. So that is how we can write that. Recently we get that the compound of argon as like this. So these are the compounds of argon. What we can have is that is what has been discovered till now. So this is how that is the very first compound which has been isolated by the Neil Bartlett is the red color compound. It is because the ionization energy of oxygen is similar to that of xenon. So the reactivity in that reaction must have been same. So that's why we get the very first compound is. Now we can write that the xenon fluoride compounds. So compounds of xenon. So compounds of xenon, we can write that compounds of xenon fluorides. So xenon forms most of the compound with fluoride, as we know that the oxygen forms its compound with fluoride. So that is why we say that the xenon forms most of the compound with fluorides. And let us check how we can write that the fluoride are formed. So by direct combination of these xenon fluorides, these that is F2, XeF4 and XeF6 are prepared by direct mixing of that is prepared by direct reaction of the elements. Direct reaction of elements, we can say that reaction of elements. So if we discuss that direct reaction of elements, we can write like this, that is the preparation methods, we can write that. So we can write that it is when xenon reacts with fluorine in presence of that is we used to say that the catalyst is used in the reaction, that is a nickel tube, we used to say that at that is 673 Kelvin. So at 673 Kelvin and 1 that is bar, we used to get the product of the reaction is XeF2. Both are mixed in the ratio of 1:1. So we say that both are mixed in the ratio of 1:1. Both are mixed in molar ratio of 1:1. We used to say that. Like that we can write that the mixing and we get the product like this. Next we can write that Xc plus that is F2. Then these F2 we used to say that is XeF4 is going to be formed. Then in that case the nickel tube, obviously all the reaction is going to be in nickel tube, that is 673 Kelvin. This is 873 Kelvin and we used to write that the 7 bar pressure. So this is the pressure, then we get that XeF4 that is formed. And here xenon and fluorine are mixed in the ratio of 1:5. So both that is xenon and F2 are mixed in molar ratio of that is we used to say that 1:5. So that is how we used to mix in the ratio of 1:5 and we get that the product as xenon tetrafluoride. This is xenon difluoride, that is xenon tetrafluoride which is formed in the reaction. So we can write like that the xenon tetrafluoride is. Next we can write is when xenon reacts with fluorine F2, then we'll write that it is in a nickel tube, that we used to write that. Now it should be the temperature should be less but the pressure should be high. So I'm going to write that 573 Kelvin but it is at 60 to 70 bar pressure. But the pressure is very high in this case. Then we get the product as xenon fluoride. That is xenon hexafluoride is formed in the reaction. Both xenon and that is F2 are mixed in the molar ratio of 1:20. So that is the molar ratio that should be used in this preparation of hexafluoride is. So that is how we are able to prepare the hexafluorides. Then we can write one or two more methods for the preparation of hexafluoride. That is, we can write that XeF2, we can write that XeF4 when it reacts with O2F2. I have told you that O2F2 is a very good fluorinating agent. So if it is a very good fluorinating agent, then in that case, even at lower temperature, the reaction will be like that because its reaction is highly exothermic. So at lower temperature, it will form that XeF6 plus O2 is liberated. That is how we can write that the preparation of the xenon hexafluoride is. So we get that the xenon hexafluoride, the recent method which I discovered for the preparation of that is xenon difluoride, one of the method which is recently discovered for the preparation of xenon difluoride, we write that it is like this. So the recent method for the preparation of xenon. So the recent method will write that the recent method for preparation of that is preparation of xenon difluoride XeF2. So let us check that the recent method for its preparation is, that is what we used to say that the salt KAgF4 that is going to react with we used to write that this is a salt what we have. When this is treated in presence of, you can use the catalyst. You can say that in presence of this BF3 it is heated. So when it is treated with BF3 and heated at high temperature, it gets converted into that is we write that KBF4. That is again a complex like this. Plus we get that AgF3. This AgF3 which is formed in the reaction is a red solid. This is a red solid which is formed. So this red solid which is formed here, then it is decomposed to give. Then we say that when it is treated with that red solid, when it is F3, when it is treated with that is xenon. So when it is heated with xenon, we get that it is xenon difluoride. We get that XeF2 is produced as the product of the reaction plus we get that twice of AgF is formed in the reaction. So that is how we are able to write that the twice of AgF2 is formed in the reaction. So this is the brown solid which is formed. The brown solid which is formed with the reaction. So Ag forms the difluoride and trifluoride, but only in case of that when it is reacting with BF3, we get the solid here, and we get that it is a red solid which is formed in the reaction, then that react with xenon to give xenon difluoride. So this is the recently discovered method for the preparation of xenon difluoride is. So that is about the xenon difluoride. What we required is, so these are the preparation methods, we can say that for xenon fluorides. The important method for the preparation of xenon fluoride is. So the main methods generally we use, right, that these three methods are the main methods in which we have to remember the ratios. What are the ratios we have to mix for the preparation of preparation of xenon fluoride is. Next we can write is, after this we can discuss about the properties of xenon fluorides. Now these are the method for the preparation of xenon fluoride is. Then we can discuss about the properties of, we can say that, the xenon fluoride is. So these are the method for the preparation of xenon fluoride, we can say that. Next we can discuss about the properties. So the properties of xenon fluoride we can discuss in the next class. That is all in this class. In the next class we can discuss about the properties of xenon fluorides and their structures of different xenon fluoride compounds. So that's all in this class. In the next class we can discuss about the properties of xenon fluorides.